Homework for chapter 25. All right, so here's our first question. It says the Andromeda galaxy is approaching our galaxy at a rate of 120 kilometers per second. Given the galaxy's present separation of 800 kiloparsecs, and neglect these other effects, let's estimate when the two galaxies will collide. All right, so there's our first problem. All right, so what we're going with. So here we go, and I've set up the first problem already. By the way, these are the only problems we're doing from chapter 25, 1, 2, 3, 6, and 7. All right, so those are the ones I'm going to go over. All right, so the first one, they give us that the Andromeda galaxy is traveling at 120 kilometers per second. So that's going to be the distance divided by the time, right? Because it's not accelerating, so that's a simple equation for velocity. And then we know that the distance they gave us in the problem is 800 kiloparsecs. So that's 800, and then I don't know why I wrote that K so large, kiloparsecs. And of course, in 1 parsec there is 3.1 times 10 to the 16th meters, and then the reason I left it in kiloparsecs is because then if this is when you multiply the 800 times the 3.1 times 10 to the 16th, that's supposed to be a 16, you get 2.48 times 10 to the 19th, and see, it would be kilometers, right? Because there's the K and there's the meters. All right, so it would be that many kilometers. All right, so once you have that, you rearrange the equation, right? D over T is equal to 120 kilometers per second. So since we have D in kilometers and the velocity is in kilometers per second, you say, all right, the time is going to be the distance divided by the velocity, right? Because the velocity is not changing. All right, so with that in mind, of course the kilometers cancel, right, in the numerator, and then in the denominator, those cancel, and so you get 1 over seconds. The seconds comes up to the numerator, that's seconds. So it turns out to be 2.1 times 10 to the 17th seconds. All right, so that's the answer. I'm going to change that to years just for the heck of it, because that gives you more of a sense of how much time that's going to be. All right, so the time, just as a reminder, is, I know I just had it on here, 2.1 times 10 to the 17th. 10 to the 17th, that's times 10 to the 17th. All right, and of course it's seconds. And so what we do is we say, all right, there are of course 60 seconds. All right, I'm not going to write all these, but this is the basic idea. 60 seconds in 1 minute, 60 minutes in 1 hour, 24 hours in 1 day, and then approximately 365 days in a year. All right, so that, you divide those things, you divide this number, 2.1 times 10 to the 17th, divided by 60, divided by 60 again, divided by 24, divided by 365, you get the number of years. Okay, so that's converting seconds into years, and so it becomes out to be approximately 6.5, it's like 5.5, and I'll just put that for the heck of it, 6.55 times 10 to the 9th years, 10 to the 9th. And by the way, 10 to the 9th can be better written as 6.55 billion years. So 6.55 billion, right, billion, just to give you a sense, years. All right, so that's not going to happen anytime soon. You're talking almost half the age of the universe, almost, right? So of course the universe is 13.8 billion years old, and so that this is starting to significantly approach the age of the universe. All right, so that's the end of number 1. Number 2, let's take a look at the problem. Oh, here, let's see, don't I have it right here? All right, so here's the problem. Number two, it says, based on the data in this figure, let's see, what figure is, okay. So here, let me open up this figure real quick so you guys can see it. Estimate the mass of the galaxy, hold on, NGC 4984. That's the one at the top. When you look at this, all right, so let's switch over to this. Hopefully it'll keep recording. Yes, it's still recording. All right, and so see, this is these are basically showing you a spiral galaxy in general and looking at the different rotation curves. Remember, this tells you that there's dark matter because these stars in the outer parts are moving too fast. Anyhow, so if we look at this, it tells us in the problem to look at let's see, at 20 kiloparsecs. All right, so here's 20 kiloparsecs, so I'm going to go straight up, and I get to NGC, what was it again? NGC, hold on, let me look back here, 4984. I think that's the one at the top. Yes, see how that's the curve at the top. So so there's 20 kiloparsecs from the center of this galaxy, right? NGC. So you just go straight up to I'm not going straight up to the curve, and then you look over and see to me that's approximately 350 kilometers per second. All right, so that's what you need this for. Right. All right. So what? And then of course, what we're going to do with that information is we're going to estimate the mass. All right. So let me pause it and then I'll write it up. All right. So from the graph at a distance for this particular galaxy, which was, I forget what it was. The curve at the top, right, was at 20 kiloparsecs, the velocity was 350 kilometers per second. I'm going to rewrite that as 350 times 10 to the third meters per second, and I also have to change the distance from 20 kiloparsecs to meters. So I'm going to use this conversion that 1 parsec is 3.1 times 10 to the 16th meters, all right? And so, kiloparsecs, that would be times 10 to the third. And then in 1 parsec, there are 3.1 times 10 to the 16th. So you multiply that, then of course the parsecs cancel. And so that gives us an answer of 6.2 times 10 to the 20th meters. So notice I've got R in meters and I've got the velocity in meters per second. Now the reason I needed to do those conversions is because this equation will only work with a velocity in meters per second and a distance R, or this is really the radius, right? This, anytime you have objects in orbit, this will determine the mass that's holding them gravitationally in orbit. So they're orbiting at a distance r from the center, and then they're moving at a velocity v. All right. So anyhow, and the velocity v, by the way, is tangential to the circle. Anyhow, so there we go. So this is going to be 6.2 times 10 to the 20th times 350 times 10 to the third, but we've got to square that, right? Because it tells us to do that right here. This is, Isaac Newton actually came up with this. And then you divide by capital G, big G, which of course is the universal gravitational constant, which is always the same everywhere in the universe. It is 6.67 times 10 to the minus 11th. So when we do that calculation, we get 1.14 times 10 to the 42nd kilograms. Now it doesn't want the answer in kilograms. It says what is the mass in solar units. All right, so we have to convert this mass right here to solar units. All right, I need a little bit more room to do that. So here we go. All right. So just as a reminder, that we're just going to use the mass of the sun, right, as we always do. So this is the mass of whatever this galaxy is. It was like NGC. Let me look real quick to see what it was. It doesn't matter. Anyhow, so this is the mass, and the mass turned out to be 1.14 times 10 to the 42nd kilograms. And so you just divide that by the mass of our sun, which we know quite well to be 2 times 10 to the 30th kilograms, right? And then that's, of course, the mass of the sun. That's supposed to be an M, the mass of the sun. All right, so notice the kilograms cancel, and so this just gives you the number in solar units. So that turns out to be 5.7. It's 5.7 times 10 to the 11th times the mass of the sun. All right, so that's usually how we talk about the mass when you're talking about an entire galaxy. All right, number 3. Let's take a look at number 3 here. It's using the exact same thing. You're using the same formula. Okay, so here is number 3. Let's see. So we're going to use. Let's see. We're going to figure out the mass to keep a galaxy now. So now we're talking about an entire galaxy that's moving at this speed, 750 kilometers per second in circular orbit of radius 2 megaparsecs around the center of a cluster. Let's see. And then, given the approximations involved, calculate this mass. Do you think this is a good estimate for the cluster's true mass? Okay, so anyhow, let's do this. It won't be the mass, the true mass of the cluster, because there's going to be a bunch of dark matter, as we've already talked about in this cluster. All right, so here we go. Where's my video? All right, so of course for number 3, we're just going to use the same formula that we just used, right? The mass is equal to the mass to hold something in orbit is equal to the distance r times the velocity of that object, and of course it's the tangential velocity. Let me draw a little picture that so that it can kind of. All right, so this is r. The mass is distributed throughout the circle, but it can be represented as being concentrated at the center. And then the velocity, this is what I mean by the tangential velocity, right? So this is the velocity going in that direction. All right, so you use this equation, right? This is what Isaac Newton came up with. Remember, the r has to be in meters, so I'm going to convert. So they tell us that it's 2 megaparsecs. All right, so the distance the galaxy is from the center of the cluster, right? So this is a cluster, like there's galaxies all over the place, and this one happens to be way out here, and put a few more galaxies. Anyhow, I don't want to take up all my time drawing galaxies. All right, so you multiply that out, and you convert it to meters. It becomes 6.2 times 10 to the 22nd, and then the velocity we just have to convert to meters per second. So that's just convert kilo time, it just becomes times 10 to the 3rd. You put it all into this equation, and you get the mass of the cluster. All right, so this is the mass of the gravity that's holding this cluster in, this is the amount that you get, 5.23 times 10 to the 44th, but of course we have to convert that to solar masses. All right, let me do that. All right, so remember, the mass of the cluster in kilograms turned out to be 5.23 times 10 to the 44th kilograms. Then we divide that by the mass of the sun, because the mass of the sun is equal to 2 times 10 to the 30th. That's approximately the mass. The kilograms cancel, right? And that leaves us in solar units. So this is 2.6 times 10 to the 14th times the mass of the sun. So this is, as I said here, the mass of the entire cluster that's holding this thing in place. And it turns out, if you added up all the mass, that would not account for this really large velocity. And of course, what's required is the fact that there's dark matter, right? There's always dark matter around galaxies. Okay, so, and in fact, we think there's, most of the universe is made